To extract crude oil, engineers must reach porous rock formations buried 7,000 feet, over 2 kilometers underground. Before a single piece of steel touches the dirt, they have to precisely map an invisible, highly pressurized trap. On land, this search begins with specialized surface vehicles, like the Vibra-sized truck. These heavy machines lower a vibrating plate directly onto the ground, generating controlled, low-frequency seismic waves that penetrate deep into the Earth's crust. This diagram illustrates the principle of acoustic reflection. As the vibration waves move downward, they eventually hit solid, non-porous barriers known as caprock. Because the signals cannot pass through, they bounce off this dense layer and reflect back to the surface, where they are recorded by thousands of installed geophone sensors. By calculating the signal's return time and remaining energy, geologists map the depth and shape of the trapped hydrocarbons hidden beneath the cap. Without this non-destructive acoustic mapping, blind drilling would simply be a multi-million-dollar gamble, risking catastrophic physical blowouts by piercing unpredictable high-pressure zones. When those reserves sit beneath the ocean floor, the operation scales up into massive floating architectures, like semi-submersible offshore platforms. Here, marine surveying replaces ground-shaking trucks with specialized ships that emit powerful, water-penetrating sound signals. These acoustic pulses travel straight through thousands of feet of the ocean column, penetrate the seabed, and perform the exact same impedance mapping as surface geophones. Whether the waves traverse solid dirt or a kilometer of seawater, the underlying physical logic of locating the hydrocarbon trap remains identical. Once the target is mapped, extraction requires the towering surface derrick. This vertical space houses the primary power transmission system, the Kelly drive. The mechanical challenge is immense. Engineers must physically rotate a segmented steel drill string stretching up to 2 kilometers straight into the earth. To achieve this, a hexagonal Kelly rod is fitted with specialized Kelly bushings. These bushings lock into the main drive shaft, transferring raw rotational power downward while allowing the rod to move vertically. This mechanical slip mitigates extreme friction and prevents localized fire hazards at the surface. At the very bottom of this 2-kilometer string sits the point of maximum mechanical stress, the tricone roller cone bit. Lined with highly reinforced tungsten carbide teeth, this bit actively crushes the solid rock strata. It is driven downward by the steel string's weight. Deep drilling relies entirely on extreme, localized force transfer, pushing massive energy generated at the surface down to a footprint of just a few square inches deep in the crust. Grinding rock creates massive thermal friction. To prevent the drill bit from melting, engineers continuously pump a highly engineered fluid, drilling mud, straight down the hollow center of the drill pipe to cool the metal. Once it reaches the bottom, the fluid flushes out through the bit and flows back upward through the annulus, the outer gap between the pipe and the rock wall. This upward flow carries the crushed rock cuttings away from the bit and back to the surface. But thermodynamics and debris removal are secondary to the mud's most critical function, hydrostatic pressure regulation. Looking at the mud column, we see the sheer physical weight of this dense fluid pushing down against the bottom of the well. This active downward force counteracts the extreme subterranean pressure of trapped gas pockets, physically holding back the gas and preventing an explosion of the shaft. Without this precise, continuous fluid mechanical loop, the active wellbore would instantly overheat, clog with debris, or catastrophically erupt. A raw borehole remains highly vulnerable. Exposed rock layers and water tables can easily collapse inward or flood the excavated shaft. To secure the shaft, the drill bit is extracted, and engineers lower a massive, hollow steel casing directly into the mud-filled well. This diagram illustrates annular cementation. A bottom plug and a top plug are loaded into the casing to perfectly sandwich a layer of wet cement slurry, keeping it entirely isolated from the drilling mud. High pressure forces these plugs downward. When the bottom plug locks at the base, the cement slurry is forced out the bottom and pushed upwards, completely filling the outer gap between the steel casing and the raw rock wall. Once the cement hardens, the process repeats with progressively smaller casings as the well deepens. This iterative process transforms a fragile geological excavation into a permanent, high-pressure industrial monolith. As the drill nears the target reservoir, the greatest operational hazard emerges: a kick. A sudden influx of high-pressure gas can blow a rig apart. To combat this, a blowout preventer, or BOP, sits at the surface. If pressure violently spikes, heavy-duty annular and pipe rams physically snap shut around the casing, instantly sealing off the explosive upward flow. With the wellhead secured, engineers often deploy advanced mud motors. Placed right above the drill bit, these motors rotate independently using only the downward pressure of the fluid flow, bypassing the need to turn the rigid mainstring. Because the mainstring doesn't spin, operators can tilt the independent motor by 1 to 3 degrees. Slowly, over thousands of feet, the flexible steel drill string follows this subtle curve, shifting the well from a vertical drop into a horizontal path, cutting straight through the reservoir layer. Horizontal directional drilling radically scales extraction efficiency, allowing a single surface rig to tap multiple square kilometers of a subterranean reservoir. Even when the final production casing reaches the target depth, the well remains completely sealed off from the surrounding oil. A specialized tool called a perforation gun all the way to the bottom of the casing. An electrical signal triggers multiple synchronized explosive charges. They detonate simultaneously, blowing perfectly neat tunnels outward, straight through the steel and the cement. Instantly, the extreme natural pressure of the subterranean reservoir forces crude oil through these newly created blast tunnels and directly into the empty wellbore. Millions of dollars and kilometers of meticulous engineering exist purely to safely facilitate this one tiny, localized explosive breach. As the crude oil flows upward, its raw pressure is caught and regulated at the surface by a complex network of safety valves known as a Christmas tree. For aging or shallow land wells with low natural pressure, mechanical artificial lift systems like these beam pumps are installed to physically pull the oil up. Extreme marine depths require a different solution. Offshore operations rely on heavy-duty submersible pumps installed deep underground to force the heavy fluid up the column. Once the safely extracted crude oil and separated gases hit the surface, they are loaded onto massive transport vessels to supply global refineries. A deep water oil well fuses acoustic geology, fluid dynamics, and brute force architecture, successfully taming the Earth's most volatile pressures to fuel the surface world.